Welcome to our milestone presentation. My name is Abdullah Enes ÖNCÜ. We are working on this project with Ramazan, MERT, and our advisors are Tuna, Tuğcu, and Fatih, Dinç. The project is based on communication of the neurons via the synaptic channel. This communication is done by diffusion. We researched about the topic on given articles and previous works of our advisors. Starting from scratch, we initially built a synaptic channel model in one dimension. Molecules are released from presynaptic end. After releasing, molecules are assumed to make a Gaussian distributed random move in a unit time. And the postsynaptic end is absorbing the molecules with some probability. After that, we added more functionalities to our model like desorption, reuptake mechanism, degradation, and glia cells. In order to see where molecules touch on postsynaptic cell, we started to implement 3D channel model. I will talk more about them. If I want to define them here, desorption is capability of postsynaptic wall to release molecules it has been absorbed. Reuptake mechanism is absorbing capability of presynaptic cell. Degradation is destruction of molecules in channel by enzymes. And glia cells are cells inside walls of synaptic channel. Also, the mathematical analysis of model took the time. First of all, we solved the diffusion equation only for fully absorbed postsynaptic wall. It was easy and solved by separation of variables of particle density function by time and position. The next work was bit complex. We solved diffusion equation for absorbing postsynaptic cell and reuptake mechanism. In order to solve it, we used term liability theory. The next case was solving for desorption and degradation mechanisms. But we only go over the existing studies done by Fatih about this case. It uses not only separation of variables, but all the Laplace transform and some complicated stuffs. We implemented all of these analytic solutions and compared with our simulations. The next case was adding glia cells to previous solution, but we couldn't do anything for it. We selected to use Python instead of MATLAB. It is because Python and NumPy is easy to use for basic calculations and simulations, and Jupyter Notebook helps us to see different states of program. We used NumPy in order to do vectorial calculations to fasten programs. On the other hand, we use multiprocessing library to make faster our simulation. When we try to run with several threads, we cannot observe any significant improvement. But when we changed every thread to a process, it was 5 times faster. It is because of limits of operating system to threads. We used LaTeX to keep our analytic solutions clear. When they are written on paper, it is only rubbish. We sometimes used Wolfram Alpha-like tools to help analytic solutions. We didn't use or develop another considerable toolchain. On the right, you can see the analytic problem definition of absorbing postsynaptic and reflective presynaptic wall. In the first realistic model we implemented a synaptic channel. The presynaptic wall has reuptake mechanism and postsynaptic one is a reactive boundary. Having reuptake mechanism means after the wall releases particles, it may absorb them back and keep them for future uses. It is one of the recycle mechanisms in synaptic channels. On the other hand, reactive boundary represents the wall which absorbs with a known probability and desorbs molecules it has been absorbed with a known rate. You can see in the figure the left wall is presynaptic wall and releases molecules from a point, and the wall can be absorbed molecules. The right wall is postsynaptic wall and both absorbs and desorbs molecules. As we can guess, the wall is not a huge receptor, but it has receptors uniformly distributed. But by some assumptions, we can think it as a huge receptor with different absorption rate. The next mechanism we added to simulation was degradation. It is a cleaning mechanism for synaptic channel. Enzymes in synaptic channel destructs neurotransmitters in channel with a rate and helps to multi-bit communication by removing effects of previous impulses. The last mechanism in our simulation was glia cells. Their one work in channels is cleaning channel by absorbing neurotransmitters with a probability. Even though glial cell mechanisms chance analytic solution so much, it is not hard to add it to simulation because it is like a postsynaptic wall without distortion. After we finished implementation of simulation and we optimized it, we started with testing it by using analytic solution. Indeed, both analytic solution and simulation tests each other. When we satisfied by the results of simulation, we started to create some figures to understand the dynamics of synaptic channel and write the paper. First of all, we test the difference between assuming the wall as a homogeneous boundary by thinking the wall as a huge receptor and assuming wall has uniformly distributed receptors with different densities. We realized that there is not a big difference between them and also the receptor density doesn't affect it. However, when we compared different distributions of receptors in the second figure, we realized that it affects the total particle at postsynaptic wall by times. When we put receptors to center of postsynaptic wall, the postsynaptic wall absorbs more particles. It is because the release point of particles in presynaptic wall is central point of it. In the next test, we do the test for saturated receptors. It means a receptor could only keep a neurotransmitter. In this case, when we increase the receptor density, absorption is increased because when we increase receptor density, the wall could keep more receptors at the same time. The last test was about effects of glial cells. We observed that glial cells has a very big effect on clearing the channel. We both were not really used to solving differential equations. So first we had to relearning it from a lecture book our co-advisor Fatih suggested. During the process we encountered many of the cases where analytic results were somewhat differentiating from the simulations. In each case we discovered the reason and arranged it accordingly. While deriving an analytic solution, we got an equation where it is not solvable by simple algebra. We used numerical analysis for deriving the roots for that equation. The simulation sometimes was so sensitive, where even on a small change the complexity would increase largely. We used space-oriented solutions and some backdoors for decreasing the complexity of the simulation, that is, the runtime of the simulation. One case of that is reflecting the particles on the boundaries was adding a huge overhead. So we used a rollback mechanism where instead of particles reflecting from the boundaries, we put them in their previous positions. This solution was proved to be correct by our advisor's previous work. Selecting the simulation time was also problematic. The small simulation time step gives better precision, but it slows down the simulation, and because step size has another conditions and dependent on simulation time, we cannot select simulation time as small as we want. Thank you for listening.